Okay, so this talk is about Elbencho, a new storage benchmark for AI et al. I called it. And I say AI specifically here because AI is driving storage systems very fast to new heights, let's say, right? Pushing storage systems and the boundaries of current storage systems a lot. But Elbencho is a very generic storage benchmark, as you'll see on the next slide. So it's not only for AI, but also specifically for AI. I'll cover the first part of the slides, and then for the second part, I'll hand over to my friend Jin. Okay, Benson was already so kind to introduce me as the creator of the BeeGFS parallel file system. I developed BeeGFS in an HPC center in Germany. So I was surrounded by users of parallel shared storage system all the time. And I saw that they were, of course, spending a lot of time already on scaling their algorithms to multiple compute nodes. But when they did that successfully, the next limit they always encountered was, of course, the shared storage system. So I saw that they spent weeks and sometimes even months struggling with the shared storage system, trying to optimize their algorithms to use the storage system more efficiently so that they could scale their compute job better. So that already showed me how important it is to give users the ability to easily check how changing your access pattern to the storage system or how changing your data format has the potential to improve your application, because sometimes after some weeks or months modifying your application, you saw that it was successful, but often enough, you just wasted that time because the change that you made did not actually improve really something, right? And this would have been a lot easier if you just would have had the tool to try out the new data format instead of going through the hurdles of modifying your actual application. But back in the days, of course, those were all spinning disk systems. So the only thing you could really try to do was to streamline your I/O in a more sequential way, use a few big files and things like that. And then at some point, late 2018, early 2019, finally, all-flash storage systems became affordable to many people with the price drops. And that opened up a whole lot of new possibilities, of course. So I found that so interesting that I joined an all-flash storage company and have been with all-flash storage systems ever since. And this was on the one hand because we had the price drop that made it affordable. On the other hand, there was also this new demand occurring, new algorithms like deep learning with image recognition, which really was no longer able to do just large sequential streaming I/O, but required very new access patterns. So why do we do benchmarking? I guess you all know that already, right? It's important to understand the storage system, to be able to predict how the storage system will behave when we change something, or to tune the system to work better for a certain application. And with the rise of all-flash systems, on the one hand, we are now able to do much more interesting access patterns efficiently to the storage system. But on the other hand, that also means that just knowing the hardware specifications of the storage system no longer tells us how fast the file system on top will actually behave for a certain workload. Because while these devices are so fast when you access them locally, accessing them over the network or through a shared file system is a whole different story. So just knowing the hardware specifications of the storage system is not enough to reliably predict how the storage system will behave for a certain workload. So all this is background of why I created Elbencho, and Elbencho is available, of course, on GitHub for everyone to download and contribute if you like. So what are the typical metrics of interest? Everyone runs different kind of workloads. You know that already, right? So there is not a single storage metric that we're only interested in. So here I'm showing a few important examples, let's say. especially in deep learning image recognition. I see it a lot that people are working with lots of small files, so they really want to read tens of thousands, hundreds of thousands, sometimes millions of files per second. Or the other case is that you have a single large file which maybe contains records of smaller image files, and want to process that through small random reads as fast as possible. And very often the latter is more efficient from the storage system perspective, but it's also less convenient because it means you're getting the images as lots of small files, and then it's the question of whether it's worth the effort of doing a transformation to a different data format every time, or if you can just continue working with the data as you got it. For databases, for instance, access latency is typically very critical. And for classic HPC systems, you have the more streaming I/O workloads. Typically, for instance, you load a large file into memory of all the nodes, that's streaming I/O, or you want to do frequent checkpoints, so that's streaming writes and things like that. All that typically with very high concurrency, based on a shared storage system. And the important thing here is while all-flash storage, other than spinning disk, generally embraces high concurrency, lots of these NVMe drives only get really fast if you access them with high concurrency. But at some point, you will also see when you add more concurrency that it can have negative side effects that you probably are all well aware of already. Like if you're running many more threads than you have CPU cores, right, then you end up with cache crashing and lots of thread switching and so on. So performance will also go down at some point. And it's of course important to be able to find out where this point is. So what can Elbencho show you? The good news is it can show you all the metrics of interest that we discussed on the previous slide. It can do this from a single client, or it can also do this coordinated from multiple clients. So here I'm just showing an example result where you can see the files per second that Elbencho was able to read in this case. The IOPS, in this case, it's the same because we do only one read operation per file. So the number of IOPS per second matches the number of files per second, the resulting throughput, and also the latency that we discussed on the previous slide. On the one hand, if you're dealing with lots of small files, then you might be interested in the full processing latency. So for small files, that would mean the time to open, read the contents of the file, and afterwards close the file. This is what it can show you. And if you're working with a single large file and doing small random reads inside there, then you're not interested in the time to open or close the file. Of course, then you're only interested in the raw reads of the file. So that's what it can also show you. And when you call Elbencho, you have the option to just provide the parameters that define your benchmark working data set. Or you can also add a number of hosts that you want to use to run it in a distributed fashion. So the results that we see here are not really impressive because I just used two VMs on my desktop for this, called Devil 1 and Devil 2, connected to a very cheap shared Samba-based storage system. But just to show you an example of how you do that when you want to run Elbencho in a distributed mode, what I avoided here specifically is MPI, because while it's very typical to use on HPC clusters, there are lots of systems out there that don't have MPI, and I didn't want to put the burden on the users to set up MPI just to be able to run a benchmark. So what you do with Elbencho instead is you start it in service mode on the hosts that you want to use as clients for your distributed benchmark, and then on one of these nodes or on some other nodes in the network, you use the hosts parameter and just specify the host names of the service, the host that you want to use for the benchmark. Or you can, of course, also have a hosts file for that. And the other important thing, because running your benchmark can, of course, take a long time depending on what you do. And when you're tuning a system to be more optimal, you will want to try lots of different settings. Some of these settings will have a positive impact on the performance, some will have a negative impact. So for Elbencho, I found it important to view live statistics during your benchmark. As you can see here, you see the progress of virtual machine level 1 and level 2 in separate lines, and also the aggregate result live during the benchmark, because when you're changing a tuning parameter very early during the benchmark, after a few seconds, typically you will see whether that was an improvement or whether that only made things worse. So if it made things worse, there's no reason to wait 10 minutes or an hour for the end result. You can stop immediately and try something else. Here are some examples of how to run Elbencho for lots of small files. What are the typical parameters that you have to specify? Probably the ones that you would intuitively expect already. There's -r or -w if you want to read or write your test data set, the number of threads that you want to use per host, the number of directories, number of files per directory, and the file size. And it's as simple as that, right? You just specify that, and then you've got good to go to run Elbencho. Another case is running Elbencho with a shared large file. And what you do there is typically you would want to create that file first. So you use the write command. Here we create a single large 50 gigabytes file. And in the case of lots of small files, what you did was you provided a benchmarking directory to Elbencho where it can create all the files. In this case, where we're working with a single large file, you directly provide the file name of the file. So that's how you would usually copy it onto the system, right, to create it in the first place. And then afterwards, let's say you want to do random read IOPS on the file. So you specify the typical parameters that you would intuitively expect. You want to read, the number of threads, the IO size that you want to use, and that it should be random IO. And here again, it's important for random reads. Typically, the result that you get after a few seconds will just be the same result that you would get after an hour of doing the random reads inside the file. So what you have here to make the time shorter is a time limit that you can add to Elbencho, after which it should terminate the benchmark run and show you the results. And specifically for AI, I found it important, or I see that people are typically not only interested in how fast can they transfer data into the host memory, like you would typically do on an HPC cluster, for instance. Instead, it's much more interesting of how fast can you put the data into the GPU memory, where you actually want to work with these images or whatever you're processing for your deep learning, for instance. So that's another thing that Elbencho supports. You can just give it a list of GPUs. This test system here, for instance, was a DGX A100 system. It has 8 A100 GPUs inside. And so I'm giving the 8 CUDA IDs of the GPUs here to use for Elbencho. And then what Elbencho will do with this parameter is it will read the data into the host memory as usual first, and then from there copy every read over to the GPU memory. So the result that you see here is really the result that you would get if you copy the data into the GPU memory. Of course, the specific result depends on the type of storage system that you have, but in general, it's the same parameters as previously. You just add the extra option for GPUs. But at some point, you will notice that you're hitting the limit that might not be imposed by the storage system, but rather by the slow data path of copying the data into the host memory first, and then afterwards doing another copy operation from the host memory to the GPU memory. So what NVIDIA came up with is a new feature or framework, you could call it, named GPU Direct Storage. This is specifically intended to avoid this bottleneck of going the extra way through the system's host memory to the GPU, and instead allows you to put the data from the storage system into the GPU memory directly, which can be much more efficient and allow higher data rates than the other approach if you really need it. And Elbencho also supports this. The new API for GPU direct storage is called QFile because the main functions in there are called QFile read and QFile write, very similar in parameters to the normal POSIX read and write functions. And the only thing you need to do to try that out once you have set up your GPU direct storage stack is to add the extra parameter --q file to Elbencho, and then instead of using the legacy data path, it will use the GPU direct storage approach. I'm not putting any results here because I don't want to take the fun away from you of finding out how much GPU direct storage can improve your own workload. And this is my last slide then. The other thing that I very often noticed also while benchmarking systems myself is that typically it's a bit boring to only see the raw numbers. Very often you're running series of benchmarks with different block sizes or different number of threads and so on. And then ultimately you're more interested in seeing a graph instead of just the raw numbers. So the other tool that I included into Elbencho is the Elbencho chart tool. To use that, you can tell Elbencho to write the results into a CSV file. And then afterwards, you can use the Elbencho chart tool to read the results from the CSV file and automatically create a chart out of that. So what I'm specifying here is that on the x-axis, I want to use the column block size from the CSV file. On the left y-axis, I want to use the throughput results. And on the right-hand y-axis, I want to see the IOPS, and then it automatically generates these graphics for you. Or with -- bars, you can also have that as a bar chart if it makes more sense. And with that, I'm handing over to Chin.
So I'm sharing my screen. Can everyone see my screen?
Yes.
Not yet.
Oh,
Okay.
no.
So can you see it, right? So I will use my desktop and I will do it here like this. So is it clear to everyone?
Yes.
Oh, okay,
Yes.
good. Okay, so Benson already made an introduction, so I'll keep it short. So I founded Zettar Inc. Our focus is to create a software data mover that moves data at a scale and a speed. I have a pretty interesting standard for scale. We usually consider petabyte routine, okay? That's what we mean scale. Speed, let's say 100 Gbps is our starting point, okay? But because it's a universal data mover, so it is capable of handling transporting data not only within a host, in a LAN, in a metro, and in over WAN internationally, and and it can handle many things like a file storage, object storage, and even local storage. Okay, so it's a universal. I will show you a DOE technical report at the end of my talk. Now, why I wanted to create this contribution to Sven's fantastic Elbencho, actually, other than what I wrote on the slide, I will tell you more personal one. Sven wrote me an email in the third quarter of last year, where we were working with ESnet on a project related to the very important ESnet 6 initiative. And I was struggling with another tool, which I will say more later on. And encountered hundreds of code dumps and read the source codes that many times too. I hated the guts, okay? And the Sven Breuner is like a fresh air in a hot summer day. I love it. So during December, in the holiday season, I asked Sven, we have been friends for a long time. I said, Sven, can I do something to give you as like a Christmas present? And how about this? And he said, sure, a graph for my Elbencho would be great. So I created one and sent him as a personal present, holiday present. But it turns out to have some practical use, so I won't say more. And it's available in the contrib subdirectory as a called storage sweep. And you say, gee, Chin, your company moves data, creates software mover for moving data at the scale and speed. Why you care about storage? I think I want to use a water transport analogy to make the point. This is a map of the famous Hachi Hachi aqueduct, transporting water from the Yosemite Hachi Hachi reservoir to the San Francisco area. It was one of the most outstanding engineering efforts in the United States in late 20th century and the early 20th century, okay? But what are the 4 key elements of the project? Let's see, okay? 1, you must have a reservoir with sufficient water. When California was in dry season a few years ago, regardless what else you do, okay? There was no water, so rock water had to be rationed. Now, what's the next? You have to have large pipes because the volume, speed, and redundancy require you must have multiple pipes. That's a real photo. It's not a fake. Now, of course, you have to have electricity to power everything. And finally, you have to have multiple pumps. Remember, that's plural. The reason is, again, the volume, the speed, and redundancy requirement. When you transport data large scale and especially at high speed, you have exactly the same logical requirements. What's the first one? You have to have fast storage. And let me turn off this guy here. So flash device. So Sven's favorite storage medium happens to be my favorite storage medium too, okay? What's the next? The next is you have to have a high enough bandwidth, right? Otherwise, you cannot squeeze a lot of water through just a garden hose, right? Same thing with the data. And the third one, you have enough computing power because everything needs to be powered, especially you do encryption, for instance, or any data transformation on the fly. And finally, you have to have a scale-out capable and very efficient data mover. This is just the same as having a well-designed, well-built water pumps for transporting large amounts. But notice the sequence I mentioned them. I mentioned the infrastructure elements first and storage being first. This is actually in the US DOE, it's called co-design principle, okay? So when you transport data at a large scale and a high speed, it's not just network along or software along. You have to have a holistic consideration of everything, starting from storage. Let me remind you one more time. Now, how do you measure the storage? Well, you do storage benchmarking. So the first, I will talk just first topic, 5 topics. How do you choose the tools to benchmark? Phil is a very well-known, even the Linux creator, Linus, okay, advocates it. But Phil has been around, but it's showing serious signs of ages because now modern data is growing really fast. Machine-generated data in one day or 1 week can make millions of people doing days or weeks of data generation, okay? So human beings are no longer dominant data generator, far, far from it. Machine-generated data is. So the field is not good filter. It's designed and released first in 2005, it's old already. How about recommendations? You want to use the latest one. Elbencho happens to be my favorite, and the storage sweep, I hope that this modest contribution makes it more useful. How about methodology? You want to do automated testing. I mean, like Sven already pointed out, okay? Oftentimes you want to do over and over again different rounds. I mean, if we don't automate, I mean, we live once, okay? Let's be efficient with our lifetime and other people's lifetime. How about what to do? Here is one thing I like to emphasize. Doing storage benchmarking is not just for fun only, okay, or for marketing or for that. It's actually to gain insight so you can improve your application, target application or application's performance. So you want to set up your benchmark application as closely as how your target application or applications interact IO patterns and the interaction with the storage. So you need a really flexible one, and Elbencho happens to meet that criterion really well. And why? Because if you don't do this, since applications reads and writes to storage and storage bench bottlenecks are really, really tough to overcome. Okay, so you better do it. So let me give you an example, which also shows you that target application, like as Sven mentioned, there are many different applications, so the standardized benchmarks won't do you any good, okay? And typically people say just depend on the storage vendors' numbers in their data sheets, which are meaningless to you, because how do you know what they created the number? How about the right now pretty well-known IO 500, that's meaningless. It's actually detrimental to your understanding of a storage system. It's very unfair. If you have most money and most powerful for hardware, you win. What does this mean? Okay, it has nothing to do with your environment, so don't trust it. So the first thing is you do is use a production data set that simulates, which you can generate using a histogram and a data generator. And the next best practice is what we shown here. Do a storage sweep, and let me show you example. This is what we created using Elbencho and the storage sweep during our work with the ESnet. Okay, the blue line is what created by Elbencho and for the test system. And so the small numbers here are GBPS. Okay, and how about the green line and the orange line? The orange line is a single data transfer run from one endpoint to another. And so you can see it's a zigzagging because it's not the average. And then the green line is created by ESnet collaborator. It's an average of 5 rounds. And how about these small numbers here? Let's take this as an example, okay? And the labels actually means the data set size and the nature. We use only so-called hyperscale data sets, which is a hyperscale data set is defined as a data set that has either more than 1 million files or overall size is larger than 1 terabyte or TB or terabyte, okay, or both. So for instance, take this as an example, 2 times 512 GB means this data set has 2 512 GB files, okay? And then together it's a 1 GB, that's it, okay? So, and then I like to, if you are curious about the data movement and its a relation about storage, now I recommend you 3 references, and both published late last year. The first one is a DOE technical report. You can get it, and it categorizes the data movements for all data-intensive endeavors into 4 categories, well illustrated, no technical jargons, and it's pretty easy to read 10-pager, okay? So we recommend it. And then the second one is the project report, and I co-authored with my collaborator, Dr. Ezra Kiesel of ESnet, and then the third one is a blog he wrote, okay, for ESnet. It's a very short and sweet. So now you are curious. What did you do with the storage sweep? I'll give you 2 examples. This is from our 2 customers in Singapore. The left one is a BeeGFS storage sweep. And when you do a storage sweep, you only need 10 seconds to issue the command. And then the rest is done for you. Whether it's a half an hour or 1 day, you don't care. You go away and do your own thing, okay? And come back and get a nice picture like this. And then this one is the BeeGFS they are trying to implement now. The other one is their 5 years old DDN running IBM GPFS or spectrum scale, okay? And look at the numbers here. The BeeGFS, about average for mid-size to large size, about 20 Gbps. How about the 5 years old? By the way, this is not running on any new hardware. It's a 3 years old. This is a 5 years old. So it's a 12. So you can see, you can easily, using the sweep graph, tell you the storage system's characteristics and the throughput for different data set. And then you can just use like a weighted average to get an overall picture for your own real data set, okay? And Sven is rapidly improving his Elbencho. So sooner or later, you can do something else. And I will do matching changes to provide more graphs, okay? So that's it. And so Again, please get the Elbencho. Sven maintains it very diligently, and I try to match. Okay, and please send back or contribute to on the issue area on the Elbencho repo. So that's it. Thank you very much. I think I made it in 10 minutes.